Hello everyone, and thank you for joining me. I am going to talk to you about the Pierian stream. Okay. How many of you are familiar with the term stream? Okay, good. That's pretty much everyone. That's what I would hope. What about Pierian? Oh no, okay. Oh, one, maybe. All right, now, this talk is on the Pierian stream, and one of these terms is very complex. So we should start with the definition. A stream is a body of running water, such as a river or creek, flowing on Earth. And that is the most complex term in this title. Now that's rather interesting, because that's, I'm sure, not the sort of stream you were expecting me to talk about. You're probably all thinking of a variety of streams. Maybe if you've had the unfortunate experience of working in Bash, you'll be familiar with Unix streams and the pipe operator. You'll have piped things from one process to another. Now, more commonly, most of us work in Scala. We need to read and write files. We're more familiar with the file streams from Java. If you worked with any kind of reactive streaming in Java, might even be familiar with the Java flow. If you work in big data, you'll have heard of Spark, and maybe you'll have used the term Spark streaming to describe some concepts there. Or if you work in distributed systems, you might use Kafka to connect things up. You might have heard of Kafka streams. So we're using this word stream in a huge number of contexts in programming. Clearly, we're not referring to bodies of water. In general, when we refer to streams, we're referring to challenges in two broad categories. One is data processing. We need to deal with large volumes of data, more than we can really fit in our program, more than we can fit in memory, maybe more than on a single machine. And so we need to deal with this iteratively. Alternatively, we might be dealing with events, things that can happen now or at any point in the future. We don't know when, we don't know how many, but when they happen, we want to deal with them. And these two fields have a lot of problems associated with them. If you're working with data, you're most likely going to be reading and writing to disk. You're going to be doing some I/O. If you're working with events, often there's a temporal nature associated with them. You're going to be manipulating time. In both of these cases, you're going to need to think about the concept of infinity. What happens to your system when there's an infinite amount of data? Not now, but throughout time. What about an infinite number of events? And usually in both of these cases, you're going to be wanting to do multiple things at once. You're going to be wanting to do things concurrently. And this in turn leads to even more problems. All right, if you're dealing with I/O, you're reading and writing files, you're going to want to manipulate resources. You're going to want to make sure that your file handles are closed. Whenever you have any I/O, you also have errors. You're no longer pure, and you need to figure out how to recover from those errors or fail if you need to. If you're dealing with events, or you have an infinite amount of events to process, you're probably going to have performance issues. You're going to need to think about any potential bottlenecks in your system, areas where you need, which are slowing your entire system down. And that might lead to back pressure, problems with a build-up of data or build-up of events. Now, if you have concurrency is rife with problems. You have issues related to non-determinism, events happening in different orders, and you need to think about all possible combinations. And if you don't think about all combinations of all possible things that can happen, you might end up with race conditions. Now, these are all very complex challenges. they're made even more complex by the fact that you can't solve them individually. When you look at these problems, let's say that you look at the problem of resources, maybe you might think you can go to a toolkit or a library just to handle resources. If you want to handle concurrency, you can go to a different toolkit or library to handle those. But in fact, when you have a streaming problem, you have to think of all of these things at once. What happens to my resources when I'm manipulating them concurrently? And so really, we want a toolkit or a library that can handle all of these things for us. And thankfully, there is one in Scala. It's called FS2. Functional Streams for Scala. This is its logo. It's a library in the type-level ecosystem, and it's based on cats and cats effect. And it lets us work with these problems in an excellent way. It gives us a data type, a stream data type, and a set of operators that work on it. And each of the operators that FS2 gives us allows us to handle a different problem in our space of streaming problems. For instance, if you want to work with infinite data, FS2 has an operator which allows you to generate an infinite stream. It's called repeat. If we want to work with side effects, i.e. things which are impure, FS2 has an operator for that. It's called evalmap. We can operate on our stream and execute side effects. And what about concurrency? There are all sorts of operators relating to concurrency. One of those is merge. Merge lets you merge two streams which are running independently together. And the really cool thing about streams and operators in FS2 is that they compose. I might have a stream. This stream has two strings in it. And let's say I want to evaluate some side effect on that stream. I can use evalmap. If I want to make this stream infinite, I can use repeat. I can chain operators continuously to create a very large structure, a large program, through quite simple means of composition. Now, I said that FS2 helps us solve all of our problems in the streaming space, and there were many problems. And FS2 helps us solve those by giving us many different operators. We have operators for iteration, fold, map, collect, operators for combining streams, merge and zip, operators for evaluating effects, all beginning with eval, all sorts of those, and also operators for dealing with time. Now, there are many, many more than I can fit on this slide. I think there are more than 100 operators that FS2 gives you for manipulating resources, I/O, all sorts of things. So FS2 is absolutely awesome, right? We can write these really, really simple streams. It's very easy to use, easy to compose, and addresses quite complex challenges. Or is it? Oh. Right, I'm going to give you an example of some code. This code is based on the life of cats. Who here has a cat? Yay. Okay, me too. This is my cat. His name is Mal. And Mal does two things. He either is very, very hungry, in which case he eats. Well, actually, there's all sorts of scratching involved there before that, if I don't feed him. But let's simplify things. He's a good kitty. He eats. And once he eats, he gets sleepy, and he wants to have a nap. So he sleeps, he naps, and eventually he'll wake up and he'll be hungry again. We're going to model the life of Mal, and also he has a friend called Popcorn. You'll see Popcorn later. And we're going to try and model that in code. Right, so first of all, let's have two functions, eat and nap. And these are both side effecting, and they just print to the console. Okay? So if I were to evaluate the eat function running the I/O, right, this would print Mal eats. If I was to evaluate nap with Mal, it would print Mal naps. So we have these two functions, right? We have side effect suspended in I/O. And I'm I'm going to plonk those in a stream. All right, so this is a stream of 2 cat names, Mal and his friend Popcorn. Mal's going to eat, Mal's going to nap, and we're going to repeat that. Now this is quite a simple program, right? 4 lines long. What do you think the output is going to be? I'm going to give you 3 possible options. All right, option 1, what gets printed to the console? Mal naps, then Mal eats, then Popcorn naps and Popcorn eats, and so on and so forth, repeated to infinity. Option 2, Mal eats, and then Mal naps, then Popcorn eats and Popcorn naps, and so on. Option 3, Mal eats first, then Popcorn eats, then Mal naps and Popcorn naps, and we keep repeating this. And there is actually a 4th option, which isn't on here, which is that it's non-deterministic. We can't predict what's going to happen. Okay, shall we have a show of hands? See how awake you are. Who thinks option 1? Okay, no hands. That's quite interesting. Okay, who thinks not option 1? All right. And that wasn't mutually exclusive, so there are a few people there who are a bit confused. What about 2? Okay, a few for 2, 3 or 4. I'm glad that Daniel's sitting right at the back, so you can't copy him. What about 3 then? All right, interesting. So I've asked this question to quite experienced programmers, some of whom have used FS2 for quite a while. And the answers that I get are quite interesting. Most people can rule out 1, but they find it very hard to pick between 2 and 3. And this is a bit of a problem, because I've shown you FS2's code. I've shown you that FS2 programs can be very, very simple, right? They're very simple to read. It is genuinely very easy to compose streams in FS2. But does simple to read mean simple to reason? Well, we couldn't answer the question, could we? Maybe it doesn't. Well, this talk isn't just about streams. It's about the Pierian streams. And Pierian means of or relating to learning. We're not just going to explore FS2. We're going to explore specifically how we learn it. Now, I've been teaching FS2 for quite a while, both FS2 and Cat's Effect, and functional programming in general. And what I've found is that when people start using FS2, they can write programs in it very easily. They can very easily write streams and compose things, and they can write programs that do what they want, or at least they think they want. But it's actually very hard for them to reason about the programs that they create. So this is a fundamental problem. And that's because reasoning is an essential part of learning. Now, what we're going to do is that we're going to explore how people learn and how people reason. We're going to look first at some code, and we're going to also look at how people reason about libraries. And finally, we'll see if we can come up with a model or a system that we can apply to reason about FS2 that will also be applicable to other functional libraries. All right, well, how do people learn? That's a very big question. It's not one that I can answer in this talk, unfortunately. I don't think that it's one that anyone has an answer to. But there are some clues. Now, if you think back to the beginning, we started off with a definition of streams. A stream is a body of water, right? It is a physical thing. And we use that word to describe lots of things in code which are completely unrelated to bodies of water. And there's a reason for that. It's so that somebody who is new to a discipline, let's say that you're new to Spark streaming or Kafka streaming, you're new to FS2, you can take what you know about physical streams and apply some of those concepts to the code that you see. So even someone who's not a programmer, right? Someone who's basically a layman, understands the term stream. They can think of streams of data. They can think of things flowing in a system. And so this is a very powerful thing. Unfortunately, analogies, while being very powerful, can also be quite problematic. They can lead to some misconceptions. For instance, being unfamiliar with streams, you might think that a stream, maybe a stream in FS2, has currents. You might think that a stream can overflow and have some idea of what that means in your head. Now, FS2 is quite interesting. If you look through the FS2 documentation, you'll see the term pipe. And when I've been teaching FS2, I've had students come to me and tell me that their pipes have burst. And definitely you can visualize that, right? But it's not analogous to anything that can actually happen when you're executing an FS2 stream. And we're sorely familiar with the problems of analogies in functional programming. If you don't know what this means, I'm not going to explain it to you. But analogies can get stuck in people's heads. Sometimes they can also hinder people from learning more. And if you can only learn in analogies, often the learning that you do is quite shallow. I'm going to quote Pope here. A little learning is a dangerous thing. You should drink deep or taste not the Pierian spring. That's from Pope's essay on criticism. And before you criticize this talk or any of the other talks in Scala Days, I highly recommend you to go and read that poem first, because he has some excellent ideas. Okay, so analogies are very good because taking something that's a physical concept that someone already knows is a great way to start. But unfortunately, it does result in some quite fuzzy thinking, and it does result in misconceptions. So can we do better? Well, I think we can. So an analogy is a really good way of building up something that's known as a mental model. Now, when you run a piece of code, when you run a program on your computer, I'll be willing to bet that you're not thinking about logic gates. Most of you, maybe there are a few exceptions, aren't thinking about your instruction set. You're not thinking about memory unless you're Rory. And in fact, what you are thinking about is a much simpler model of the way that your computer actually works. And that's because you don't need to know everything about your computer in detail to predict the output of a program. You can cope with a simple model. It will help you understand the code. So that set of concepts that you do have in your head when you're thinking about a program being executed is known as a mental model. It's a simplified set of concepts that you use to reason and predict the way that your code will work. And there are ways of building those. One of those is experimentation. This is something that I do with people a lot when I'm walking through FS2 code. Okay, now, I presented you with a challenge, right? A challenge of this stream here, and I asked you to make a prediction about what would get printed to the screen. Now, I'm sure that some of you are thinking, why do we have to predict? Why don't we just run it? And in fact, you can, right? I can take this stream and I can run it and I will get an output. I can even tie that in with predictions. I can use the scientific method, right? I can start with a model, make a prediction, run an experiment, and see if my prediction was correct. And if it's not, if I don't get what I expected, and by the way, this isn't what some of you expected, I can go back and refine that model. So experimentation is a really powerful technique. It's something that you can do independently, which actually suits quite a lot of people, right? I can go and take this code, I can go and run it, an experiment, and write many, many experiments myself. And that suits me. I love experimenting. But there are some problems with experimentation too. Now, with a library like FS2, there are so many operators and so many combinations of things that you can possibly do that, in fact, to get a good model via experimentation, you need to run a huge number of experiments. For instance, what if I tweak the order of this code? What if I put the repeat first? Would I get a difference in behavior? And doing all those experiments, all those combinations of operators, is quite cumbersome. Not only that, there are some things that we can't do via just experimentation. We can't reason about concurrency. And that is because any experiment you run when you're dealing with concurrency doesn't have a completely guaranteed output. You can't say, I'm going to run the experiment again and get the same result. And even if you think that you're getting the same result, try running it on somebody else's machine. Try running it in your production systems or on your CI machines. Or on the 1st of January, right? You can have all sorts of problems which relate to concurrency. So experimentation, it has a lot of pros. It's certainly much better than just relying on analogies, but it has some problems associated with it too. Now, thankfully, in functional programming at least, there's quite a well-established mental model for how we reason, and we can use that along with experimentation. How many of you would consider yourself functional programmers? Okay, that's great. Now, I want you to try and think back. This may bring back some traumatic memories, but think back to your early days of functional programming, to the first few pieces of code that you wrote. Maybe you used a book, something like the Red Book or Essential Scala to start learning. Who used the Red Book of functional programming? Oh yes, okay, we all share this trauma. Me too. Now, the way that you learned would have been to write many, many functions, many small, pure, referentially transparent functions. These words are all ringing a bell. And also to write some small algebraic data types. And when you did that, you were building a very specific mental model in your head. It's one of substitution. And the mental model of substitution is quite straightforward. If you want to reason about a piece of code, which is an expression made up of functions and values, just substitute a function for its body and evaluate. Here's how you might evaluate get or else. So I have this expression, get or else. It's a function, and so I'm just going to substitute it for its body. And that happens to be a pattern match. And mentally, I can walk through this code in my head now. I can walk through that pattern match, see what's matched, and get a single value out. So by following this series of steps, by substituting and evaluating, I can reason that this piece of code will evaluate to the string mao. And that's very interesting, because I can do this without even needing a computer. I can do this with a pen and paper, provided that I know what my code base is. In fact, this is completely different to what a computer is actually doing, right? It's not as though when you write a pure function in Scala, your computer just changes modes now, and it's now switching to a substitution evaluation mode. There are languages where you can do that, and it is very cool. But Scala is not one of them. Under the hood, you still do have a processor. You still do have an instruction set, right? You have a stack and a heap. But you don't need to think about those things, right? The model that you need to think about in order to get the correct result can be one of substitution and evaluation, one that's very different to what happens under the hood. Okay, so this is a very straightforward set of steps. Not only is it straightforward, it's also consistent, right? There's no fuzziness associated with it, unlike analogies. So maybe we're on the right track here. Let's try and apply it. Okay, this is the code that we started with. We're trying to reason about this code via substitution. So I'm going to go and look in the FS2 code base, and I'm going to substitute. All right, if I substitute stream, I get this, pull.output. Now let's try substituting a val map. Okay, some more code. There's a flat map in there, so that's interesting. Perhaps a slight sense of dread for some of you. Let's substitute again. Okay, and what about repeat? Of course, repeat does something an infinite number of times. Okay, so yeah. Now this would work, right? It would work. If I kept doing this, if I kept looking at each function in FS2 and substituting and substituting and substituting and evaluating, I would get somewhere. I would be able to make a prediction, but it would be incredibly difficult to do. Not only that, it would lead me right into the internals of FS2, into a very interesting place, I may say, right? If you look into the internals of FS2, you'll see all sorts of wonderful concepts. You'll learn about laziness, about co-data, which is very cool. You'll even learn about free interpreters and DSLs. So it's a very interesting journey, but it is one that also requires a lot of effort. And I would say that at the end of that journey, it is one that I've taken personally as well, I'm very proud to say. You would know enough not just to use FS2 to write streams, you would know enough to contribute to it. Which is great, but that's also perhaps more detailed than what we actually want, right? Our goal here is to use FS2 to solve the more challenging problems in the streaming space. And ideally, we would be able to do that without needing to learn about the way that its internals worked. And I should add, by the way, that the authors of FS2 also don't want you to look at the internals, right? They do have documentation, and they don't expect you to walk through the code in order to figure out what's happening there. So we're on the same page. Okay, so evaluation and substitution, this model, it's very good because it gives us a set of steps that we can apply, and it's consistent. There's no fuzziness associated with it. And we can use it to make predictions. And it is one that is taught in functional programming. This really is the fundamentals of functional programming. But unfortunately, we can only really use it on small functions. We wouldn't want to use it on libraries. We don't want to be exposed to the internals of the way that libraries work. Okay, there are other really interesting things that we can do in functional programming. Okay, this is one that I absolutely love. It's called equational reasoning. Now, I can talk about the operators in FS2, repeat, let's say, in terms of other operators. So instead of diving into the operators, I can describe how they relate to each other. For instance, I can tell you that repeat is equivalent to the double plus, the append operator, an infinite number of times. I can also tell you that append, the double plus, relates to a val map in some ways. A val map actually distributes over append. Some of you who are functional programmers or have been in that space will have heard the term distributivity. Okay, so distributivity means that if I have two streams and I append them and then a val map, that's the same as eval mapping the first and then appending that to the eval map of the second. All right, and I can use equational reasoning to prove things. All right, this is how I might prove something. Let's say that I have a stream mal. I want to prove that if I repeat that stream and then evaluate something, eval map eat, some effect, that's the same as taking that stream, calling eval map and repeat. So the order of these two operations doesn't make a difference. I can do that using equational reasoning. I can expand out repeat into a load of append operators, right? I can then use my second law of distributivity to condense that, right? To now apply val map within those. And then finally, I can use my first law that relates repeat to append to then condense that once again. And I proved, right, through equational reasoning, that my first statement was equivalent to my second. And that's absolutely beautiful. And of course, I would expect everybody, right? Everybody who uses FS2 should be able to do this too. That's not the case, right? This form of reasoning suits people who are very mathematical. If you've done a mathematics degree or a degree in science, perhaps, and you like proofs, right? If you're the sort of person who in their spare time will go and look at Coq and Agda and Idris and all those other fun, interesting languages, you'll love this approach. But most people aren't like that. Oh, by the way, I forgot to introduce Popcorn. This is her. She's a flat-faced Persian, and she's absolutely lovely. All right, so this form of equational reasoning, it's lovely, but it goes over most people's heads. We wouldn't really want people to need to do that to reason about FS2. It is consistent, though, just as our evaluation and substitution model was. And one thing that's quite good about it is that we don't see any internals, right? We don't now need to go and drill into the FS2 code. All right, so where does that leave us? We want to try and reason about streams and reason about FS2 as a functional library. We've had a look at analogies. We've seen that people do learn through analogies, but they can be problematic because often they can result in some quite fuzzy thinking. We've had a look at experimentation. We've seen that it's very helpful. It's a necessary tool, something we should all learn to do when we encounter a new library, but it alone isn't really enough. We've looked at the model of substitution and evaluation in functional programming, the one that we learned when we started functional programming, and we've seen that it is very helpful for small pieces of code, but not when it comes to reasoning about something as complex as FS2. And we've also looked at equational reasoning, things that relate our operators to each other in FS2. And we found that while it does work, it's far too mathematical for us to expect to do it on a regular basis. So it would be good to try and find a better model, something that had the best of all worlds, right? Can we have a model that has a physical analogy, so we can get started with it quite easily, gives us a set of steps, so that we can apply it in a straightforward manner? I want my model to talk about operators and composition. I don't want it to drill into the operators. And finally, I want it to be able to predict behavior for all future pieces of code I see. Oh. And this is quite a difficult task. This is, by the way, a very large version of a Feynman diagram. And if any of you are familiar with Feynman diagrams in physics, you'll know that they're very magical. And you needed to be Feynman to come up with them. More specifically, we're in a bit of a catch-22 situation. And that is because if you're trying to learn FS2, you don't know about the way that the internals work, but you want a simple model. But if you already know FS2, you don't need a simple model, because you already know how the internals work. This is the case with lots of functional libraries. And so what we're really looking for is some kind of way to meet in the middle. All right. Now, I've been teaching FS2 for quite some time now to people who have a variety of different experiences. Some of them are quite junior in their functional programming journey. Some of them are experienced functional programmers, but they still have challenges reasoning with FS2's code. And over time, I think I've probably got a model which seems to work. We describe FS2 streams not in terms of streams, but in terms of the idea of a pull. Now, when we see a stream in FS2, if we want an element from that stream, we pull on the stream. And pulling is a bit like asking for an element. So you're asking the stream for an element. It may not necessarily give you one if it doesn't have any. we pull on the last operator of a stream, and each operator, let's say eval map or repeat, these are operators, will pull on the operator above it. It might evaluate some effects on the result that it gets, and then it would output its result. Or maybe it doesn't actually have anything to output. It would tell whatever's downstream that it was done. I'm going to try and explain this in pictures because I'm quite sure that those steps weren't quite enough to cover it. Okay, so a pull, let's try and represent that as an upwards arrow. So a pull is requesting an element. An operator might output an element. We can represent output as a downwards arrow with the thing that we're trying to output. So in this case, our element is the string mal. And if we're done, let's represent that with a tick mark. Okay, so how can we use that to reason about streams and operators? Well, let's take a look at this one. So this is just a stream of mal and popcorn, 2 elements, 2 strings. A stream only ever emits something if we pull on it. So we start by pulling. We pull on this operator, and the first thing that it outputs is mal. If we pull on it again, it'll output popcorn. And if we pull on it again, it'll output done. So we can draw a little timeline of all the operations and that will happen. What about our other operators? Let's take eval map. This is the simpler one. When we pull on eval map, it'll pull on whatever's above it. And if whatever's above it outputs an element, let's say it outputs mal, it'll evaluate whatever effect it has. And in this case, the eat effect, it'll print mal eats to the console. And then it'll take the result of that effect and output that downstream. What about repeat? Repeat is a bit of an interesting one. So if we pull on repeat, it'll pull on whatever's above it and receive an element. And let's say it receives mal. It'll just send that downstream. If we pull on it again, it might receive another element. If it receives popcorn, it'll send that. But what if when we pull on it, and repeat pulls on its upstream and receives a done, it will recreate the stream that we're trying to repeat and start pulling on the beginning of it again. So what we'll actually see if we were downstream would be mal, right? Our stream wouldn't terminate. Okay, so these are some examples of operators. We can draw diagrams for them. Can we compose them? And the answer is yes. It is actually quite easy to compose these diagrams just by slotting the arrows together. So this is a diagram for the code that we saw in the beginning, a stream eval mapped with eat, eval map, nap, and repeat. Right? This is the same piece of code. We can slot all of our diagrams together and follow the arrows to figure out what side effects get executed in what order. And this is very good, because it takes a bit of work, but it does give us a precise sequence of steps. There's no fuzziness associated with this. We can describe composition, right? How operators fit together. And also we can use new operators. If I was to give you an operator in FS2 that you hadn't seen before, let's say I was to give you take, you could ask questions, right? What does it pull? What does it output? When is it done? And you can use those questions to reason about the way that take works and fits into your entire stream. Now it is limited. There are many, many concepts in FS2 that aren't in this diagram. We haven't talked about errors, for instance. We haven't talked about resources. But it's possible to extend it to think in terms of those. Now, one challenge, which is very difficult, is reasoning about concurrency. And that's because concurrent thinking requires its own frame of mind. You need to be very good at reasoning about combinations. But in practice, it works quite well. All right, so we're almost at Pierian, right? We've almost got our knowledge. We've looked at streams. We've got a definition of them. We know the challenges that are associated with them. And we've looked at different ways of reasoning through analogies, experimentation, the different mental models in functional programming. And also, we've had a look at the pull model, a way of looking at streams in FS2. And I'm presenting this as though it's revolutionary, by the way. If you look at the FS2 documentation, you won't quite see these diagrams. But it's not quite. Actually, this kind of term has been used within FS2 for quite a while. And even if you were to look on a broader scale, right, outside to other functional libraries, even different frameworks, you'll see the use of models. One great example of the use of models, perhaps, is regular expressions. When you think about regular expressions, I'm pretty sure you don't think about the engine that's actually executing them. You have a much more general and simple view of how to compose them. I've just talked about FS2 here, but actually I think that this can be applied more broadly to other functional libraries. We can start thinking about composition of our operators. Quite ironically, once I start working through this pull model with people, they tend to become better at reasoning about FS2's code than they do about cat's effect. It would be interesting to see if we could come up with a model which would also work for cat's effect. What about other libraries which are based on composition? What about optics libraries? I should be able to describe optics without thinking about glasses, for one thing, as an analogy. But I should also be able to describe them without talking about profunctor lenses. There should be a middle ground that we can meet. All right, if you want to dive deeper, explore both mental models and streams in more details, I've got a ton of resources for you. There's this wonderful paper called All Things Flow, which is a great paper on the history of streams. If you're interested in notional machines, or mental models, also known as notional machines, in functional programming, there's a great book called How to Design Programs. If you're interested in mental machines that may relate to streams, there's another lovely paper called How to Design Co-Programs by Jeremy Gibbons. I don't think we can really talk about learning cat's effect without mentioning Adam's wonderful book, Essential Effects. So definitely go and check that one out. And if you want to learn more about FS2 and streams, you can go and read my blog. Perhaps there might be something on the pull model on it. All right, thank you.